Okay, so in the interest of time, let's start the second session for this morning for ammonia combustion. So now we will have a lecture from Professor Thibault Guiberti, who is assistant research professor at CCRC at KAUST, and we'll talk about the fundamentals of ammonia. You can start.
All right, thank you very much. Am I audible? Yes? All right, good morning, everyone. My name is Thibault. I've been at KAUST for 8 years now doing my research. And for the last 3 to 4 years, with a strong focus on ammonia and hydrogen combustion. And I'm very happy to have this opportunity to give this lecture on ammonia combustion fundamentals. Actually, it's very comfortable for me to go just after Professor Kobayashi, right? Because he's basically already explained to you why ammonia is a promising fuel for future power and mobility applications, at least some of them. And he's already explained what are the challenges and limitations of ammonia, specifically low reactivity, low flame speed, and large propensity to produce NOx. So if we ever want to have efficient and safe and clean gas turbines, for example, using ammonia, in terms of R&D, we have to go through all of this. Okay? We have to understand the chemical kinetics, and Professor Sarati will talk a lot about this tomorrow. We have to understand very fundamental flame properties, such as the flame speed, and Professor Kobayashi talked about this. But before we can really go into this, sorry, this is quite inconvenient. Before we can really go into this quite complex turbulent flames with very complex injection strategies in the turbulent flames, in the gas turbines, such as these swap flames, we have to do all these flames that are in between here. I guess I'll stop use this. We have to work all these flames that are in between that are not so simple that at least they start to include some of the effects that are important in practical applications, such as turbulence, but they are not too complex, such as a gas turbine, so that at least we have a chance to understand what's going on. And so for this presentation, I'll be mainly focused in this area here with these intermediate flames in terms of physical complexity. All right. And so I've chosen to separate this lecture in 2 parts. The first one is basically on how ammonia's chemistry influences the way the flame looks, because it is important, and also how it influences the tools we can use to study it. So I'll talk again about the species that are relevant to ammonia chemistry. Of course, there will be some overlap with what has been told before. More details on the role of electronically excited species. What are the challenges and opportunities for optical diagnostics? And I'll just give one example of a measurement campaign we've done at KAUST to reveal the potential of chemiluminescence, so flame spontaneous emission, to do flame sensors in the industry. And as a second part, I will talk about what I said before, all these canonical flames that we do in the labs to try to bridge the gap between very fundamental flame property and chemistry and practical applications. And first, I will show why laminar flame speed / laminar burning velocity, it's just different terms for the same thing, is not telling the whole story. It's very useful to know, but that's not enough. And then I will list a few examples of these canonical burners, canonical flames that people have been studying to understand how we can then, in the future, do practical applications. Right, moving on to the first step. What are the species relevant to ammonia chemistry? So that's just a quick reminder, because Professor Kobayashi talked about this, but in this presentation, very often I will start to talk about methane, which we use as a very simple reference fuel, okay, to then compare with ammonia. So this is a model of the reaction pathways for methane oxidation. So, oops, sorry. So if we have methane here, as you start to oxidize it, the fuel will degrade, CH3, go through intermediate radicals, such as formaldehyde, reacting with OH, with CO to get one of the products, CO2. So you've seen this before. And basically, it means that there are some intermediate radicals that are very useful to study if we want to understand what happens in the flame. For example, formaldehyde here marks the preheat zone, where the flame starts to degrade the reactants. Then OH reacts with formaldehyde to produce heat release rate, so it informs where the flame is. And this is also what CH does. If you mark where CH is, you get to know where the flame is actually burning. And so people have been using this in labs, okay, to try to study the instantaneous structure of turbulent flames to understand turbulent flames. And if you use techniques such as planar laser-induced fluorescence, which Professor Aldin this afternoon, I'm sure will talk a lot about this one, you can image instantaneously where these species are in the flame. And for example, we see that in blue here, we'll see where the layer of formaldehyde is. This is where the preheat zone of the flame is. In orange here, we will see where the CH is, which is the reaction zone. And in red, we have the OH. Sorry, I'm not able to show very well what I want to show because this is actually very inconvenient to use. But yeah. All right. But the issue is that with ammonia, it's totally different chemistry. Right? If we look at the similar reaction pathway diagram for ammonia, we look at different species. Ammonia, as it starts to degrade, will form NH2 to NH, and then produce some NO, and with reaction with OH, also will go through the final products N2. Okay? So now if we want to do something similar, image the relevant species to look at the flame structure, we have to target different species. We can't target formaldehyde and CH anymore, they are just not present. Right? And so that's why we had to develop different techniques, this still relying on fluorescence, but this time on different radicals, NO and NH, to study the instantaneous structure of flames. Okay? So different chemistry, it not only controls how the flame burns, but it also controls what we have to do in the lab to understand these flames. Another way to kind of look at the same thing is not using laser, just to look at the flame. Okay? So if you just look at the flame, and I will illustrate this with a basic lab-scale swirl burner. So this is a burner that you find in a lab, a few kilowatts, that starts to have a flow field and a complexity that mimics a gas turbine. Okay? So turbulence and swirl. So this is just an example of such a burner. And if you use it to stabilize methane flame, typically you'll see blue flames. Okay? This, from left to right, you have different equivalence ratios, different air-fuel ratios. And at the bottom, you have what you'll see with an ammonia flame. And so these are real colors. You'll see exactly this with your eyes. And clearly, they look very different. One is blue, one is orange. And we know that these colors, they are the signature of electronically excited species. Okay? Species that are at a level of excitation that they don't like. Okay? They want to go back to ground state, and to do this, they release photons, light, and this is what we see. Okay? And basically, if we have different colors, then it means we have different electronically excited species, which means we have also different ground state species. And this is just another way of showing that we have very different oxidation pathways between ammonia and methane flames. Okay? And so this leads me to the next section about the role of electronically excited species. So Professor Kobayashi started to talk about this, but for ammonia, there's a lot of potential application from this. Again, let's go back to a reference flame. What you see here on the right is a turbulent methane jet flame, okay? Real colors, so typically you'll see it blue, and you see it blue because the excited radicals that are in methane flames emit in the blue. So one way to study this in the lab is to use a spectrometer that records the light, diffracts it into the different wavelengths, the different colors, and every time you see a peak in this spectrum, then it means you have an active species emitting some light. Actually, for methane flame and most flames, there's a lot of activity in the UV that's due to OH star. Okay, so star means electronically excited species, so excited OH. But you can't see this because it's in the UV. But we see that in the visible range, around 432 nanometer, we have CH star, right? And this is the culprit, okay? This is the responsible species for the fact that the flame looks blue. And there are other little peaks that we are going to discuss after, okay? Like C2 star. And so clean methane flames, they radiate basically blue light. So how can we explain this more carefully? People have been able to model this to describe the reactions, the chemical reactions that explain how these excited species they are produced and consumed. And these are just examples. So for OH star, for example, there's a list of reactions that are important, and each of these reactions is assigned 3 numbers. These are the Arrhenius coefficients that you can use in this model here that dictates what's the reaction rate, the speed of this specific reaction. And this is as a function of temperature. But if we look at the different reactions that this model describes, there's one that says that if atomic hydrogen meets atomic oxygen and a third body partner, M could be anything, there's a chance to produce OH, but at an excited level right? So this reaction is basically exothermic NOF to produce OH, but directly excited. If there's carbon in your stream, there's another reaction that can do the same thing. CH plus O2 gives OH star plus CO. Okay, so that explains why you end up having this excited species. Like I said, they don't like to be excited. They want to go back to ground state. They want to go back to rest. And one way they can go to ground state is by releasing energy under the form of photons. Yep. And so this is reaction number 3. OH star goes back to OH plus H nu. So this is an energy. H is the Planck constant, and nu is the wave number. So it's related to the color of the wavelength that is being sent. And just quickly, that's not the only way for the excited species to go back to rest. It can also do it non-radiatively, just by colliding with species that are around, such as oxygen, water, or H2, or any other species. You collide, you transfer some energy, and you're not excited anymore. So with a model like this, we can explain why we have OH star. But of course, there's a similar model that explains why we have CH star, so then why the flame is blue, and why we have C2 star. So these are just the basics, and this explains why the methane flame is blue. But we can do something similar for ammonia flames. And these are examples of spectra recorded in an ammonia flame. Okay, so that's spontaneous emission spectra, which sometimes I will call chemiluminescent spectra. That's somewhat similar. And the one on the left focuses basically in the UV, and the one on the right focuses in the visible range. We see in the UV that we also have, for ammonia flames, OH star being active. Here it doesn't say star, there's this notation here, but it's similar. Okay, you can replace it with a star. But we have additional species that were not present with methane. We have NO star, NH star, and then we start to have this very intense broadband contribution in the visible range that kind of continues here all the way. And okay, there's a lot of species that contributes to this, but mainly this is NH2 star. Okay? And because this is broadband in the visible, and the eye of the human is actually very sensitive in the orange, that's why we actually see the ammonia as an orange flame. So I talk about all of this because the signature of light of an ammonia flame is actually very rich. There's many species that contribute to this, and this is actually an asset. Okay? It's useful to know this, because if it's very rich, then it means there's a lot of chemical information that is coded into it. And probably if you study this light very well, then we can infer a lot of things about the chemistry. Basically, we can do flame sensors. And I will explain how this can be useful, especially when we start to deal with complex blends, ammonia methane, ammonia hydrogen. So this was mentioned before also. Ammonia doesn't burn very well. Potentially for some application, it is useful to blend it with something more reactive. Methane as a first step, but to be purely carbon-free, maybe with hydrogen. Okay, do partial cracking of ammonia. Okay. So I've started basically to hint into an opportunity for optical diagnostics. So I'll go into this section of challenges and opportunities for optical diagnostics. So I think it will be okay for you to tell me why do we care about the flame luminosity, right? In an engine, in a gas turbine, we don't see the flame, right? And whatever it's blue, green, or yellow, what matters is that it burns and produces high enthalpy species. Actually, what's nice about this is that recording the light from the flame is actually very cheap compared to other techniques, such as probes and lasers. And the data you get is quite easy to analyze. And the only thing you need to be able to potentially achieve this is some optical access to the flame. Right? Just a little hole in your combustion chamber. Of course, in labs, that's very easy to do. More complex to do in practical applications, but this can be done as well. Okay, so what can we specifically learn from this chemiluminescence, except just saying this is blue or green or orange? And to illustrate this, I will use a very simple domestic example. Again, not talking about ammonia for now, but natural gas. Okay, so essentially, before we all had electrical stoves, we had stoves fueled by gas, potentially natural gas or propane or butane. Okay. So if you've seen these kind of systems before, normally if the system is well set up, you'll see some kind of a dark blue flame. Okay. But if your system is not well set up, you might be seeing a flame that is lighter in color and with a hint of green. And I said before that these colors, they are due to the CH star and C2 star excited radical in the visible range. And quantitatively, if we look at this, So we can think that this flame, well set up, probably is burning at stoichiometry, right? The right amount of fuel and air so that you have no fuel wasted and perfect oxidation. And this is a typical spectrum for a stoichiometric flame. We see that in the visible range, the largest peak is CH star, okay? Dark blue, 432. As you start to put fuel in excess, so not enough oxidizer, this is what we call rich conditions, we see that the C2 star peak becomes prominent. This one is in the green, and so if you mix basically blue and green, you get this kind of color. So someone who knows about this, so a stove technician, just by looking at the flame can tell you this flame has fuel in excess, you don't want that. Potentially you're wasting fuel, but more importantly, you might be producing carbon monoxide. Okay? You don't have enough oxygen to fully oxidize your fuel, you get CO instead of CO2, and we all know that CO, carbon monoxide, is toxic. Okay? So this is really just a basic example that is domestic, but you can think that this can be applied to practical devices as well. Okay? If you learn from the flame what the color means, you can know if your flame is what you want or not. So this was an example for carbon monoxide, but there are other sources of emissions that you want to take care of. And one of them is NO, nitric oxide. Okay? And these graphs here show simulations of the NO concentration as a function of the equivalence ratio, right, the fuel-air ratio, in ammonia air flames or methane air flames. And in orange, you have the temperature as well. So we've known for many decades already that in gas turbines fueled with natural gas, you want to operate here, lean, large excess of air. You do this because you reduce the temperature, you do not activate the thermal NOx pathways, and then you get not a lot of NO. You try to do the same in ammonia flames, and Professor Kobayashi mentioned it, you fail. Okay? You have thousands of ppm of NO. Because in addition to these thermal routes, you have also fuel routes that are actually very active when it's lean. And alternatively, for ammonia air flame, you want to operate slightly rich. Okay? This is where you don't have a lot of NO. Of course, if you operate slightly rich, you have fuel in excess, you are at risk of wasting the fuel. So then you have to do what he called this two-stage combustion, rich then lean, to take care of the remaining fuel. So again, just to say that clearly knowing the equivalence ratio and controlling the equivalence ratio is the key of controlling the NO emissions. But knowing exactly what's the fuel that is burning is also important. You see in a graph like this, measurements of the NO concentration in the exhaust in thousands of ppm as a function of equivalence ratio. But you have different curves here, different symbols, because there are different compositions of the ammonia-hydrogen blend. And we see clearly that changing the composition, even though you're always using ammonia and hydrogen, has a huge impact on the amount of NOx you're producing. Oops, sorry. So the key of this slide is saying, okay, accurate knowledge of the equivalence ratio and the fuel composition is critical for emission control. And I haven't talked about this, but clearly also for flame stability. So these things are important. And again, you may be able to ask me, okay, but isn't the operator of the gas turbine or the engine, for example, choosing the amount of air he sends and the amount he or she sends and the amount of fuel? So aren't composition and fuel-air ratio prescribed and known? Okay. Why do we care about this? It's actually because we don't really always know exactly what's burning and how it's burning. This is an example taken for natural gas, again, always using this reference of methane or natural gas. This table shows variations of composition in the natural gas in British Columbia in the mid-80s. Okay, so just an example. But this basically shows that as a function of season or city, you have basically 90% plus or minus 8% of methane in your natural gas. And it's the same for all the different components. So you don't really always know exactly what you get. And it's even worse if you start to consider gasified biomass. Okay? If you have biomass residues that are available to you, you can send them into a gasifier and convert them into a biogas that is typically composed of hydrogen, CO, CO2, methane, and other hydrocarbons. And depending on the type of biomass you have access to, you'll get a different composition. So depending on the season, for example, then you might, as a gas turbine operator, if you are fed by the gasifier, you might not know exactly what you burn. And trying to come back to the topic of today, which is ammonia, there's a similar situation with the cracked ammonia. I said already, you probably want to have some hydrogen in there to boost the reactivity. One very good way to get it is by partially cracking some of your ammonia. And one very efficient way to do this, technically, is to use catalytic cracking. And a curve like this shows you the cracking percentage of ammonia. So 0 means you've cracked nothing. 100 means it's all converted to hydrogen and nitrogen as a function, as a function of the temperature of your catalyst bed. Okay, different colors means different catalyst composition, but that's not very important here. And this curve is so steep that it basically shows that if you don't control exactly what's the temperature of your catalyst bed within a few degrees, you might have very large variations of the composition of your exhaust gases of the cracker, which is then sent to the gas turbine. Okay? So again, just examples to show that as an operator, we don't always know exactly what we are fueling the turbine or the engine with. Okay, so temporal variations of fuel composition are to be expected. This was for the fuel composition. What about the fuel-air ratio? And I will illustrate this with the schematic of a powertrain of a micro gas turbine, which this one is from Ansaldo. I guess those of you who did the lab tour yesterday, you've actually seen this turbine. So the heart of the unit is the combustion chamber here, produce hot products that are expanded into a turbine. So it creates a rotation of a shaft, and this is connected to a generator that produces electricity. But in addition to this, on the shaft, there is also a compressor that sucks in the air from the room, compresses it, and sends it to the combustor. Okay? And so the key here is that we don't have a mass flow controller where we push a button and we say, I want 10 kilograms of air per second. Okay? It's kind of passively driven by the speed of the shaft. Okay? And it changes with time depending on how the turbine is operating. And it gets worse than this. Once the compressed air goes to the combustor, this is a schematic of the combustor, it comes from the top here, and then not all of it goes into the injection, goes into the flame. Some of it goes into these dilution holes that are here to make sure that the hot product from the flame, they are cooled down before they reach the turbine. Otherwise, it's too hot and you damage the turbine, right? And here, again, we don't have two mass flow controllers that speed the flow. We just have holes, so it's all passively driven using pressure drops. And it's okay, it's the same, we don't really know exactly what's going to happen. And even worse again, once all this air reaches the injector section, some of it goes into a small pilot flame that burns in diffusion mode. Some of it finally gets mixed. Sorry, this is very inconvenient to use. Some of it gets mixed with the fuel, but actually we keep some pure air to inject at the very last moment, okay? And that's a protection mechanism because we want to make sure it's not flammable until we want it to be flammable. This is a flashback protection mechanism. And so when we do this, we really mix all the fuel and air at the very last minute, very last moment, and we're not sure it's fully premixed. And so you might have actually spatial variation of fuel-air ratio, equivalence ratio, in your combustor. So again, we don't really know exactly what's burning and how it's burning. And this is why I'm talking about these flame colors, because by looking at these flame colors, we get to know potentially what's burning and how it's burning. And this then allows me to move to the next section, which is about an example of measurement campaign we've done at KAUST to reveal really the potential of this chemiluminescence, these flame colors, specifically when there is ammonia in the flame. Yeah, the objectives were simple. We wanted to measure largest possible database of flame luminosity for ammonia methane flames. We did also ammonia hydrogen, but today I'll talk only about ammonia methane. And then use this database to really try and understand how these chemiluminescence intensities, these colors, they can be surrogates of important flame properties we want to know, which is, for example, fuel composition and equivalence ratio. And for that, we've used a very basic burner that was mentioned as well this morning, a counterflow burner. Okay, so that's a very specific burner in the lab. It's basically two nozzles facing each other, and these two nozzles, they're identical. And they feed the same mixture. Oops, sorry. A ready-to-burn mixture of methane, ammonia, and air, sent to an injector, two injectors facing each other, so you get a stagnation plane in the middle, and on each side of this stagnation plane, you get two identical flames, we call them twin flames. And what's nice about this burner is that the flames, they are very flat, which means they are very easy to study and to model. And the small deviation we did from the standard burner is that we pierced the hole at the bottom here, so that the light emitted by the flame could escape, be focused on an optical fiber with a parabolic mirror, and then sent to a spectrometer so that we can really analyze the light distribution from the flame. So we did this exercise for as many flames as we could do. And this is just an image that shows that we varied the fuel composition. So this one on the left is pure methane, it's blue. The one on the right is almost pure ammonia, it's orange. And you have all this rainbow of colors in between. So these are real colors. And so we were surprised at the beginning, but other people have seen the exact same thing. And we can also, for a fixed fuel composition, vary the equivalence ratio, okay, the fuel-air ratio. And we do also observe that this changes the flame color and the flame intensity. For each of these flames, we have a spectrum which we can analyze. I've kind of shown this one or an equivalent of this one before. This is the one for pure methane, contributions from OH star, contributions from CH star. The one for ammonia, I've shown also, contributions from OH star, NO star, NH star, and these broadband contributions. Where it gets interesting is when you mix ammonia and methane. When you mix ammonia and methane, of course, as expected, you see some OH star, because it was there for ammonia and methane. You see some CH star, you see NH star, you see NO star, that's expected. But we do find some peaks that we did not find before. Okay? And this, by doing some literature review, we were able to attribute them to excited species CN star. Okay? And why is this important? It's important because it highlights that there are basically synergies between the reaction mechanisms, some cross-contaminations, okay? Because you can't get CN star if you have only methane or if you have only ammonia. You get them only if you mix them together, right? So it basically shows that these reaction mechanisms, they don't work in isolation. Sometimes they communicate. And this is just highlighted here with an electronically excited species. But if this is true for an electronically excited species, that's also true for the ground set species. Right. So then we have all these flames, all these spectra. Each peak, we can quantify it, and we can plot curves like this. This is, for example, the OH star intensity as a function of the equivalence ratio for the different compositions of the blend. So if it's black, it's almost pure ammonia. And as you go up like this towards the red, you put more and more methane. Okay? Clearly, the more ammonia you put, the least OH star you get. Why not? What's nice is that when you look at the same graph, but for NO star, we get very different trend. If you start for pure methane, almost no NO star, you put a little bit of ammonia, NO star explodes. Then if you put too much ammonia, NO star decreases. Okay? So we have different trends for these radicals. And if we look at all the radicals we have access to, they all have different trends. And again, this is very useful, okay? Because if they all behave differently and we record them, there's probably enough information in there to predict, to recover what was actually burning. Okay? Except that now we have 5 inputs, we have these 5 radicals, and there are 2 quantities we care for. We want to predict composition of the fuel and equivalence ratio. So this might be quite complex and nonlinear relationships. And this is where maybe machine learning regression algorithms, they can help us, okay, to uncover these complex and hidden relationships. So we have basically this database. In this case, we had 214 flames. And we chose to put 75% on the side that we are going to use to train our algorithm, and 25% to keep on the side for future validation. So we have this algorithm that injects as an input all the different colors from the flame, as well as the equivalence ratio and the ammonia fraction. And you want to train it to basically predict what was the equivalence ratio and the ammonia fraction just by using the different colors from the flame. And if we look first only at the blue points, these are the points for the training data, we show that we are successful on collapsing on this unity slope line, okay? So the algorithm was able to recover what was burning. But what's nice is that when now we use the 25% of the data that was not used for training, these are the red points, we also fall on this line. Okay? So the predictions, they were successful, which means physically that there's enough information in the light that the flame sends to really predict, to understand exactly what's burning in terms of fuel composition and equivalence ratio. And that's the foundation to be able to say that we can probably use this to do flame sensors in engines or gas turbines. And we can do this because this light signature is so complex. The issue here is that we've only done this for these laminar flames, which are very different from what you'll find in an engine or in a gas turbine. And as very often as when you do machine learning, you always ask yourself, okay, can this be generalized for other conditions? And other conditions in this context means more practical flames. And so to challenge this, we've done different flames, this time turbulent swirl flames, so not quite a gas turbine already, but something that mimics quite well the flow of a gas turbine. So that's an example of the flame. So we did, again, methane ammonia. And the other deviation we did from the laminar flame study is that this time we used a bench spectrometer, a much cheaper and easy to use spectrometer compared to the scientific grade spectrometer, with the assumption that maybe in the field, in the industry, they would use bench spectrometers instead of scientific spectrometers. We recorded all of this data, and then we sent as inputs the light emitted from the flame into our machine learning algorithm, not telling the algorithm, of course, what was the equivalence ratio and what was the ammonia fraction. And we found these green symbols, okay, that are for these swirl flames, that again match very well this unity slope curve. So we were able to predict the equivalence ratio and the ammonia fraction in these gas turbine-like flames with an algorithm that was only trained with laminar flames. So this is where the story stops here, but it basically shows that there should be enough physics to develop these flame sensors. So this was basically an opportunity for optical diagnostic thanks to ammonia, but I haven't talked about the challenges yet, so I'll just backtrack a little bit, go from D to C, and talk about some challenges. So this I've shown before. If you want to image in a lab the structure of a turbulent methane flame, it's useful to image formaldehyde, OH, and or CH. Okay? Fortunately, you can't use these same species in an ammonia flame because they're not just, except OH, they are just not present. So you might want to target instead NH2, NH, and OH or NO because they have similar behavior. And these techniques here, when you do this imaging, you actually have to choose lasers that are tuned specifically for this species. So if you have different species, you have to go back to the drawing board. You have to figure out new lasers or new excitation strategies for this species. And this is what I'm going to talk about very briefly, because I'm sure there will be much more about this afternoon. So this is just a schematic of the experimental setup we have used to do NO-NH laser-induced fluorescence. So you have an ammonia flame here. This is a big high-pressure combustion duct because we cared for this study about elevated pressure flames. So you've seen this in the lab yesterday. And so what we do is that we shoot in this flame two different lasers, both in the UV, but one at 236 nanometer and one at 303. And one is targeting NO, and the other one is targeting NH. Why is that? Is because if you want to excite the species to generate this fluorescent signal that you're going to record with the camera to measure your species, you need to make sure the species accepts this wavelength, okay? It's tuned to this wavelength, and this is what this diagram shows. These are measured leaf excitation spectra for NO and NH. You see peaks there. There are many options to excite NO near 235. You can choose any of these peaks, but you need to be around this wavelength. And there are many also peaks that you can choose to excite NH, but this is around 203 nanometer. And just to look specifically at the numbers, you have to be accurate within a few picometers to be able to access this species, right? If you're off, you don't interact with the species. Okay. So that's one example of what we had to redevelop, basically, to be able to image the structure of turbulent flames when this is ammonia. So this is what we observed. In red, you have the NH layer. This is where the flame front is, turbulent flame front, and NO marks the post-gas region, the post-flame region. And again, I'll be very brief on this because I'm sure it will be talked about this afternoon. So this is what Professor Aldin developed at the University of Lund. So you want to be able to image NH2 as well. And again, it was just to illustrate that if you want to excite NH2, there's only some specific wavelengths that you can use to excite it efficiently. And they had to use a very specific laser technology to access this wavelength, 285, with the right levels of energy. And they were able to prove that you can image the location of NH2 in these flames. All right, so I'll stop here with part one and move on to part two, which is somewhat disconnected. This is about these canonical flames that people have used in the lab to try and bridge the gap between what's been done that's very fundamental, but very useful, and all the other end of the spectrum with practical applications. Okay? There's all this limbo in between where we need to work a lot. And I will illustrate why we need to work a lot on this with the first step, why just knowing the laminar flame speed is not enough. And a very nice study that people have done in NTNU in Norway to illustrate exactly this is this one. I'm going to talk about this. So my point is that knowing the laminar burning velocity is not sufficient if you want to predict what's going to be the behavior of the flame in a practical combustion device. And among other things, one reason for this is the turbulence, the effect of turbulence. The laminar burning velocity doesn't take this into account. So they showed this very nicely by using a burner, which was very simple. Okay, the only thing it had special more than a laminar flame speed burner is turbulence. So you have a ready-to-burn mixture of ammonia, hydrogen, and air that flows through a tube at a velocity that is large enough for it to be turbulent. And before the injection, it meets this shape here, this bluff body. And this induces a recirculation zone so that the flame is stabilized like this. So on the side here, you have the flame front, and you have in the center a hot recirculation of burn product. And this is very useful because you keep sending back to the incoming reactants hot products, and so this is a continuous ignition source. And in an instantaneous fashion, this is what it looks like. You really see that this is a turbulent flame with some corrugation and some potentially localized extinction. So what they've done with this burner that was very clever is that they chose two flames, M1, M refers to methane, and A1, which is an ammonia hydrogen air flame. But they tuned the composition and the equivalence ratio so that they have the exact same, almost the exact same laminar burning velocity, thermal flame thickness, and abatic flame temperature. So in terms of laminar properties, these two flames, they should be identical. Okay? And then they challenged this in the turbulent burner, and so they looked at lean blowout limits. They started with these flames, which are both, so let's ignore all the points except M1 and A1. So both are 0.6 equivalence ratio, and if you start with very low velocity in your burner, you have a stable flame, you progressively increase the velocity up until the point the flame can't take it anymore and extinguishes. And this occurred at around 10 meters per second for the M1 flame. And what they've noticed is that if they do a similar exercise with the A1 flame, they could pass much, much, much larger velocities up until 120 meters per second. Okay? So although these flames from the laminar point of view, they are the same, one of them, the ammonia hydrogen flame, is much, much more resistant to blowout. Okay? So that's just a clear indication that even if you know your laminar burning velocity, this is not enough to predict what's going to happen in an actual practical burner. And I will explain to you later with a different study why this happens. Okay. And so now we'll go through different studies made in different parts of the world, showing how people can specifically choose a physics they care about, study it with a very carefully selected burner, and so that in the end, by adding all of this together, we can potentially do practical devices. So clearly, there's a need to study flames for more realistic operating conditions. What I mean by this is higher turbulence levels and also elevated pressure. Okay, most practical applications, they operate at elevated pressure. But we want the flames that we choose to study to remain sufficiently simple so that the flame physics we care about, at least we have a chance to look at it and understand it, right? You can't work directly in a gas turbine. That's too complex. All right, and that's why people, they spend a lot of time choosing specific burners that are purposely built to every time isolate a specific physics. And the first study I want to talk about comes from a collaboration from NTNU and TU Darmstadt in Germany. And they've used, again, one of these canonical counterflow burners. So that's similar to the one I've talked about before. You have two nozzles facing each other, supplying the same ready-to-burn mixture of ammonia and hydrogen in this case, and you get these very nice twin flames in between. And so they did this because they wanted to subject the flame to strain in order to mimic some of the effect of turbulence without having all the complexity of turbulence as a first step. So what they did is that they progressively increased the velocity in these nozzles. This is what you get from left to right, which basically increased the strain in these flames. I will explain what strain is. And you see that these flames are getting closer and closer together. So from a schematic point of view, if you have your two nozzles here and here, okay, you have the stagnation plane in between and a flame on each side. These arrows, they are the streamlines. Okay? Because there's this stagnation plane, the gas you send has to deviate and escape at some point. And as you increase the velocity in the jet, these streamlines, they deviate faster and faster, and you're actually increasing the strain. Okay? And the strain, what it is, basically, it is very connected to the flow timescale. And increasing the strain actually decreases the flow timescale. It decreases the time available for the chemical reactions to occur. Okay? You're kind of pulling the reactants apart, and they may not have enough time to react. That's what you do when you increase the strain. And so what they've done in this study is for all these different compositions, they progressively increase the velocity, increase the strain, until every time, at some point, the flame dies. And they were able to quantify this metric here, this RSIB, which is basically a metric that quantifies the resilience of the flame to strain. And they did this as a function of equivalence ratio for different fuels. And they were able to show clearly that all these ammonia-hydrogen mixtures, they were much more resilient to strain than a methane flame. Okay? And we can use this knowledge to explain what happened before with the bluff body burner. Okay? So strain mimics somewhat some of the effects of turbulence, because what turbulence does, you have all these turbulent eddies, these little vortices, that are kind of separating the reactants, okay? They're creating this mess where reactants, they are moving away too fast and may not have enough time to react. And this is what you do when you strain the flame. And clearly here they show that a methane flame doesn't like to be strained compared to an ammonia hydrogen flame. And this is why the lean blow-off limit for an ammonia air flame was much larger than a methane flame before in the other study from NTNU. Okay. And physically speaking, why is that? It's because of the presence of the hydrogen in the blend. Okay? Hydrogen is so light that it diffuses kind of everywhere very quickly. So it always goes where it's needed. So it helps the chemical reactions to occur in due time, even if they don't have a lot of time to occur. So this was one example. Now I want to talk about another example, which is about the effects of the stoichiometric mix of fraction on the behavior of jet flames. So what's the stoichiometric mixture fraction? So first, what's the mixture fraction? The mixture fraction is the ratio of the mass of fuel you have to the mass of oxidizer, okay, at a specific time and location. And the stoichiometric mixture fraction is this ratio when it is stoichiometric, the right amount of both reactants. And I want to see the effect of this in turbulent jet flames. Turbulent jet flames, they are very useful in the lab because they are very nice canonical objects that we can study. They are very nice. But they also have practical applications in furnaces, ovens, or flares, for example. And in labs, at least, we typically get these flames using very simple round tubes like this. These are just 3 examples. So we'll have high-velocity fuel flowing in the center and being injected in an environment with oxidizer, potentially quiescent or low-velocity air, for example. And these are examples of these turbulent jet flames. Again, this reference always with methane or this one also ethane, different pressures, different jet velocities. We see that these flames, they have different colors. Some of them are attached, some of them are lifted. Okay? Some of them stay really on the rim, some of them are what we call aerodynamically stabilized. And of course, we can do a similar exercise with ammonia hydrogen jet flames. There's 2 images here. One on the left is time average. This is what your eyes would see. But of course, these flames, they are turbulent. Right? If you use short exposure, you see that the turbulence plays a role here. All right, so if we look at this aerodynamically stabilized flame, they kind of suspend on top of the burner and they stay there. Right? So they find suitable condition for stabilization. And we can image this with laser diagnostics. You have 4 images here. There are 4 different realizations of the same thing in this lifted methane flame. And the different colors are different scalars, metrics that we measured. The red is OH, which we measured with OH PLIF. And it basically shows you where the flame is. And you see these tongues here, these red things, that are basically showing that you have the edge of the flame, the most upstream location of the flame, that is floating in the field. Around the red, you see this black, okay? That's the formaldehyde. it tells you where the preheat zone is in between the flame and the unreacted fuel. And then in the green, we have the mole fraction of methane, right? So we have a jet of methane in air. On the right, you have nothing, it's air. And so in between, there's this mixing layer with different concentration of air and methane. And so what you have in yellow is the location in this reaction layer where it is close to stoichiometric. And what's interesting here is that we always see, for these 4 images, that the flame is really sticking on top of this stoichiometric layer, right? The flame is looking for the stoichiometric mixture fraction line. This is where it likes to sit because it is stoichiometric. This is where it's most reactive. And of course, the flame also needs to find a location where the velocity of the field matches its velocity of propagation. Okay? So these are the 2 criteria that you need to meet to find where the flame will be. Okay, so why do we care? So this is a schematic that I borrowed from a study from the group of Professor Kobayashi, where you have this fast jet fuel, a slower air stream separated by the nozzle. So the blue lines are the streamlines, and the black line and the red line, they are the stoichiometric contours, where it is stoichiometric. And you have 2, one for methane and one for ammonia methane. E equals 0.3 refers to the fact that 30% of the energy, the calorific input of the blend comes from ammonia, okay? So there's one way to define the blend. That's why you have 0 here, there's no ammonia. And so clearly what strikes here is that these 2 lines, they are not at the same location, okay? Why are they not? Yeah, I'm not sure what's happening now. Why are they not at the same location? You can understand this by looking at the global combustion reaction when it's stoichiometric. You've seen these equations already this morning. The one for methane here tells you that now if you take the mass ratio of methane to the ratio of oxygen, you get a ratio, mixture fraction, stoichiometric mixture fraction here of 0.2. If you do the same exercise for ammonia, you get that relatively speaking, you need more fuel in mass compared to methane, okay? And this explains why this red curve is on the left, okay? Because you have this mixing layer with pure fuel on one side, pure air on the other side. If you need to find, relatively speaking, more fuel, you need to go towards the jet of fuel. And we see that because the fuel is typically faster in these applications, as you go closer to the fuel, you find higher velocities, right? And this has a tendency to push the flame downstream. Okay? And these researchers in Sendai, they've actually measured that, right? They measured this standoff distance, dA, and they've plotted it here as a function of the different compositions in the blend, right? So from blue to yellow, you get more and more ammonia, and clearly we see that the flame gets further and further away from the nozzle. And why is it important? It's because of temperature. They've also measured the temperature at the tip of this nozzle, and they saw that as they switched progressively to ammonia, the flame gets further away, which means that the nozzle gets colder and colder and colder, okay? And this is just a canonical study, but that's important for practical applications because if you design a burner for methane, for example, and then you change the fuel, because of these reasons, the flame might displace a little bit, and you may get a different temperature of the nozzle. Here it's colder, but it could be hotter. And of course, it might damage your unit if you have not really planned that the flame will get closer and that the nozzle will get hotter. So this is, again, one example of very canonical lab-scale study that is useful for us to really understand what happens on a fundamental level and then to develop predictive models for practical applications. All right. Next example, dual fuel injection to enhance combustion control. So I said before, you probably want to partially crack some of the ammonia to introduce some hydrogen to be more reactive. And once you've done this, probably a good idea to consider maybe not remixing hydrogen and ammonia and use this opportunity to inject maybe your reactants more cleverly in the burner. And that's what we wanted to try and challenge at KAUST. And so we've used this burner, we've developed this burner, which is conceptually quite simple if you look only at the center line. This is just a typical swirl burner. So you have a ready-to-burn ammonia air premixture that flows through a swirler, and then inside of this red pipe goes to the injection chamber and burns the flame. Okay, so that's a normal burner. But then what we've added is that around this, we have another tube, this one that is filled with hydrogen and air, already ready to burn, that goes to a different swirler, and then also goes to the injector on the other side of this red tube. So you have two concentric jets here. And what we can do is that we can keep this red tube very short, recess distance 100%. Basically, all streams, they mix again inside of the burner, and it's as if they were mixed from the beginning. So you end up with this normal premixed burner. But you can keep the tube very long, keep things very separate, stratify the reactants at the outlet to get very different behavior, hopefully. And just to highlight that we've measured the stratification using Raman, you see here radial profiles of the different species that we measured. The orange is the ammonia. So if you have, the fuel tube fully recessed, this profile is almost flat, so it's kind of homogeneous. This profile, this is hydrogen in blue, this is almost flat, almost homogeneous. But if you just change the length of your tube, you get a situation where in the center you only find ammonia, and on the edges you only find hydrogen, right? So you have an homogeneous case and a stratified case. And we wanted to see what's the effect on the flame. We chose an equivalence ratio for ammonia that was slightly rich. This is where you want to be if you don't want to produce too much NOx. For the hydrogen, we chose very lean. This is also where you want to be to produce not a lot of NOx. And we changed nothing else except the length of the tube. And these are the flames we got. And clearly, we see that these flames, they are different. The homogeneous flame is more compact than the flames where everything is stratified. But if you've listened to what I said before, also, we see that we have very different colors, which means that things are burning differently. And on the right side, we clearly see that at the bottom, it's blue. This is an indication this is where the hydrogen is burning. And so the hydrogen flame is at the base, and it kind of stabilizes another flame at the top, which is orange, because this is mainly where ammonia burns. And the specific question we wanted to answer in this study is, can we use this to influence thermoacoustic coupling? So the first speaker of the school mentioned this. If you have very powerful turbulent flames, you have acoustic waves in the combustion chamber. If you're not lucky, they resonate with the acoustic modes of your chamber. Everything gets amplified, and you can damage your system. Okay? And it's probably a good idea to see if we can mitigate these thermoacoustic instabilities. One way to measure these instabilities is to put a microphone in the combustion chamber and plot the spectrum of noise. Okay? And we've done this for 3 flames, the homogeneous one, the fully stratified one, and one in between. Forget about the green curve, look only at the red. You see that if the flame is typical, like a fully premixed homogeneous, we have strong thermoacoustic instabilities at 113 Hz and 226. And as we progressively increase the size of this tube to stratify the mixture, we see that these peaks disappear, basically. And so by being clever about how we inject our 2 fuels, because now we have this opportunity, we have 2 fuels, we're able to show that we can control the thermoacoustic coupling. Yes. Sorry, it's kind of a catalog of studies, but that's kind of by design. So the next one I want to talk about is the turbulent jet flames that we've studied at elevated pressure, specifically to validate combustion models. Again, the first speaker of this school mentioned this. It's becoming so expensive to run actual tests of actual gas turbine you develop or engine that people rely more and more on numerical simulations. Okay. Before you can trust these simulations, they need to be validated. And one way to validate them is to choose target flames where you do simulations and experiment and you double check if the simulations are correct. And this is an example of that, specifically for flames that are including ammonia, high turbulence, and elevated pressure. So we chose these jet flames. You have 2 here, one labeled 14 and 128. It's basically one has 14% of the ammonia being cracked. The other one is 28%, so there's more hydrogen in there. And we chose to go at 5 bar to replicate the pressure you find in micro gas turbines, so small-scale gas turbines. And so to achieve this 5 bar, we had, of course, to put this flame in the high-pressure combustion duct that we have at KAUST. To validate the simulation, you need to compare metrics, compare numbers, okay? And different metrics, scalars that are important to compare when you deal with ammonia. One is NO, okay? So you have to measure NO. And we measured NO in this flame using quantitative NO leaf. And Gaetano Magnotti is going to talk about it this afternoon as well, I'm sure. So I'm not going to talk more about this. And you also need to compare, to challenge the simulation based on temperature and major species, which we measured also in the lab using Raman scattering, which is a very different physical mechanism for the diagnostics. And again, Professor Magnotti is going to talk about it. So we've measured NO quantitatively, major species, and temperature. Okay. And we chose this flame, and that's important because these flames, they are very simple boundary conditions, very easily very accessible optically. Okay, so easy to measure, but also easy to simulate, right? To do these comparisons, measurement simulations. Yet they have turbulence and they have high pressure. Okay, so that's very good for model validation. So then, some people, for example, the group of Professor Wong Im here at KAUST, they did the simulations of this flame. These are large eddy simulations. From afar, looks that predictions are very good, but we have to look really into the details. And with this data, what we could do is that we could check the simulations for their predictions of the radial profiles of NO concentration. Black symbols are the experiments. You have different heights going up above the nozzle, 2 columns for the 2 flames, and the red are the simulations. And we see from this that in terms of numbers and trends, simulations are doing a pretty good job, which basically tells you that the model as it is today can be trusted for its predictions of NO in this practical-ish application. But you also learn that close to the nozzle, maybe there's some effort to do because the model is not perfect there. They've also looked at temperature and major species in mixed fraction space. Okay, not as a function of the radius in the field, but as a function of mixed fraction. So I said it before, mixed fraction 0 means you are in air, mixed fraction 1 means you're in the fuel. So if you are in the middle along this blue line here, you are stoichiometric. This is where actually the temperature is very high. Here, the black symbols, they are the measurements. And you have 2 types of simulations, the red and the green. The red is the one with unity Lewis number. So it means that they've treated the diffusion of species, such as all the species, they diffuse exactly at the same speed. And this speed is the diffusion speed of the heat. Okay? Unity Lewis number, equal diffusivity. But they've also done simulations where they've allowed each species to diffuse at its own speed. It's called mixture average here. And what's interesting is that if you look, for example, here close to the nozzle at temperature, both models fail. You would want a model that's kind of in between. But if you go very far from the nozzle, actually the simpler model, the equal diffusivity, works well. But you can't really say that's the best model because at the same location, if you look at hydrogen, it does very badly. And actually, you want to allow the hydrogen to diffuse at its own speed to be good. Okay? And so the learning from this is that clearly now these modelers, they know they need to have some kind of a hybrid model that is able to basically weight average and balance between these 2 diffusion models to predict the truth. And there was no way for them to know this if they did not have access to this data. All right, so numerical treatment of species diffusivity must be improved. Okay. And final study, I did not check when I started, so I have time. Okay, good. So again, a study from Lund, where they subjected the flames to extreme levels of turbulence. Okay. The issue with the flames I've talked about before, they are turbulent, but you can't have extreme levels of turbulence because if you try to increase the jet velocity, increase the Reynolds number, the flame, they detach and they die. Okay? So they use specific burners, which are somewhat similar in principle. You still have a high velocity jet of fuel and air in the center, but now it's piloted. All right? They have around the flame basically a laminar methane flame that produces hot product that keeps the flame attached, keeps igniting the flame at the base. And they chose to look at 2 different burners, which are in principle similar, but they have different turbulent properties. So extreme levels of turbulence in the context of this study means very high Karlovitz numbers. Karlovitz number is the ratio of the chemical timescale to the turbulence timescale. Here, the chemical timescale doesn't change. They are looking at ammonia air flames, the same equivalence ratio. Okay? But as they increase the turbulence intensity, they decrease the turbulence timescale, so they increase the Karlovitz number. That's just one metric to quantify your turbulence, let's say. With one of the 2 burners, these are the kind of flames you get. Right? From left to right, you have more and more turbulence. Practically speaking, it just means you have more and more velocity in your jet. We have access to the field of the location of the reaction zone measured with NH3. I've talked about this before. And people were able to do the same in the simulations. And what's interesting is that here, as we increase the turbulence, we see that this NH layer gets thicker, gets broadened. Okay? That's evidence that these flames, they are broadened by the turbulence. And what is very nice is that we see that the LES captures this. Okay? So again, this informs the modelers that they're doing a good job. And why this happens is that if you have the turbulence that is intense enough, typically it means that the smallest scales of the turbulence, they become smaller and smaller. And eventually they become smaller than the width of the reaction layer. So they can go inside, mess with it, and make it thicker. And the models are able to predict this. But when they try to use their different burner, operates on the same principle but have different turbulent properties, they did the exact same thing. They increased the turbulence intensity, but they did not observe at all this broadening. What they observe is more corrugation. You see here the flame is not flat at all. It is very corrugated. Okay? And we see that the simulation, they also predict this. And what's happening here is that even though the Karlovitz number is very high, the turbulence is very high, but here this time, it's just because the vortices basically they turn very fast, but they are not small enough to go inside of the reaction zone. They are bigger, and so what they do is that they corrugate the reaction zone. Okay? And again, the learning is that their model is very good because it's able to predict these two regimes very well. All right, so I've reached the end. We've learned how ammonia's chemistry influences the way the flame looks, and I hope that I've shown that it's not only just for show. Okay, we care about what the flame looks like, and also it influences how we can reveal its structure in the lab. And then we've reviewed a few examples of very purposely built ammonia flames in labs that are selected to really understand more and guide the design of future combustors. And I'll stop here. Thank you.
Any question for Professor Thibault? One, okay. Oops, sorry.
Yeah, you have the two.
Hi, thank you, Professor, for this excellent talk. My question is about N2O, which has a global warming potential that is about 300 times of CO2. So is there a way to quantify N2O in canonical flames?
Yes and no. We know very well how to measure N2O in the exhaust of these gases, and so we've done this before. But non-intrusive, local, and time-resolved methods to measure N2O, I think this is more challenging. I mean, there's someone in this room that knows much more this than me, but I don't think there's any technique, laser technique right now that we can use that is very efficient to excite N2O and to make it fluoresce. I may be wrong, but I'm interested, and yet I don't know how to do this. Yeah. But yeah.
Maybe I can comment on this. We're actually trying now very hard to work on measurements of N2O, and it seems possible to use sensitive Raman setup with multiple pass, which should be possible to go down to that level. And also measurement in the infrared region using degenerate forward mixing, using a sensitive transition seems possible, but it's not too easy.
Okay, good. So if Professor Aldin says it's hard, then it's hard. Yeah.
He said it's not too easy to be.
Yeah, well, it's yeah.
Other question?
Professor Thibault, thank you for a very interesting and insightful talk. I have a question about a plot that you showed on slide 31, which I'm not sure if we're able to show now, but
Looks like I've lost.
basically had the laminar flame speed, and you were able to make conclusions on the lean blowout limits. I was just wondering about how you were able to make these conclusions.
You said 21st?
31st.
31st. Yep.
Yeah,
Sorry,
that's the one.
I was focused on changing the slides. Can you repeat, please?
Yeah, so you were able to make conclusions on the lean blowout limit. I'm just not sure how I can see them on this plot.
Okay, yeah. So this is as fast as you can push the flow, 10 meters per second, before you lose the flame for this equivalence ratio, right? And we are lean, okay? So that's the lean extinction. Actually, maybe I was too fast, but here they've fix the equivalence ratio and increase the velocity, but you can use the same exercise when you fix the velocity and you progressively decrease the equivalence ratio until it becomes too lean and the flame dies. Okay, so basically the flame here dies because it's too lean. Okay, so that's why it's called the lean blow-off. Okay, and so these two flames, A1 and A2, for the same equivalence ratio, one survives a faster flow, but you can look at these points as well, where you can see that for the same velocity, one dies at a much leaner. Two ways of doing the same exercise, right? And in both cases, the A flame, the ammonia hydrogen flame, is more resilient.
Okay, that's very interesting. I just have a quick follow-up. So this blowout behavior, is it usually attributed to the chemistry of the fuel, or is it a combination with the physical aspects of the burner as well?
Yeah, it's everything. So the chemistry of the fuel and the turbulence. So in a burner like this, typically what happens is, so I told you there is this recirculation zone inside that brings back hot product that keep igniting the flame. If turbulence becomes too intense, it locally extinguishes the flame, okay? Too much strain, not enough flow time for the chemistry to occur, okay? So it creates a hole, and now cold reactants, they go through this hole, they fill the center recirculation zone, and you basically remove this continuous source of ignition. So, so the chemistry depends on your fuel, but the turbulence depends on your burner, the velocity and its geometry.
All right, thank you.
I have a follow-up question on this slide, because when you presented this slide, you said that, okay, can you put it back again?
No, I think it's my computer.
Okay, sorry. So you mentioned that you will be able to explain why, when we change the fuel, when you move from a methane flame to a blend of hydrogen and ammonia, you can extend the velocity at blow-off, or you can decrease the equivalence ratio.
Yeah, so I tried, so I guess I failed. But so
Okay,
my attempt to do this was to use this study. So in this study that doesn't have turbulence, they strain the flame.
Okay, so but yeah, I know the answer, but just you didn't go back to the previous slide,
Yeah,
so
sure,
I just wanted to make the
but so
close the
then
loop.
for everyone. So clearly here they show that ammonia hydrogen flame, they are more resilient to strain than methane flame. Okay, so you can reduce the time they have available for chemistry, still they burn. Okay, so now we can go back, connect again to the previous study where you have this bluff body burner, where increasing the turbulence basically kill the methane flame faster than the ammonia hydrogen flame, and that's for this reason, because the ammonia hydrogen flame is more resilient to having this chemical time reduced, this flow time and this chemical time reduced.
Thank you. Any last question for Professor Thibault? Okay, so if there is no question, thanks again for the really nice talk.